Greetings and welcome to Distillate. In the previous class, we discussed how to solve a combustion related problem. So the only trick or the only method that I told you was that draw a block diagram and then complete the block diagram. You need to complete whatever information is required in the block diagram. And once you do that, you will be able to do any other problem easily, right? You don't need to really give too much uh, effort for other parts, right? So you just need to complete the block diagram and just then you can manipulate that information, whatever you have from the block diagram to get the values, right? So once we have done that, so let's move on to a few more problems today. All right. So let's go on for example number 2. A coal containing carbon 67.9%, hydrogen 4.4%, sulfur 0.8%, nitrogen 16%, oxygen 7.9%, ash 4.5%, and moisture 12.9% in weight percent. All these things are given in weight percent. All right. Remember, usually for solid fuels, all these percentages that are given, they are usually by weight. All right. About the composition of a solid fuel, it's all usually given in terms of weight, right? Weight percent. And when we talk about gaseous fuel, then, and even sometimes a liquid fuel, it's usually in terms of mole percent. All right. But for solid fuels, it's always, if it is not mentioned over here, still you can say that it's weight by weight, right? Unless and until it's given that it's volume by volume or mole percent. Fine. So the dry product of combustion analyzes carbon dioxide as 14.5%, oxygen 4.7%, and nitrogen as 80.8%. This is volume by volume. That is, this is the mole percent. So calculate all these things. So we are going to draw a block diagram for the same. So this is my furnace. All right. Over here, I have coal that goes in. So remember that this is in weight by weight, that is weight percent. So my basis is going to be 100 kg of coal. Correct. It's going to be 100 kg of coal since it's weight by weight. If it would have been mole percent, then I would have taken 100 kilomole, right? 100 kilomole of coal, right? So for now we have 100 kg of coal. So carbon is going to be 67.9 kg. 67.9 kg. So carbon is 67.9 kg. Then hydrogen is 4.4 kg. So these are all the composition that was given about the coal, right? I have not mentioned ash here again because again we don't require ash as such for our calculations. So unnecessarily we will not fill our block diagram with values, right? Then there's air coming in, of course. There's air that will be coming in. We don't know anything about this air, so I'll let it be. Then over here in the flue gases, we'll have carbon dioxide, we'll have unreacted, we'll have nitrogen, then we'll have unreacted oxygen, then we are going to have, since we have sulfur here, so we'll have sulfur dioxide as well, and we have moisture, of course, so, and we also have hydrogen, so we'll get water. All right. There has been no mention of carbon monoxide, there has been no mention of incomplete combustion, so we are going to assume that the combustion has been complete and all the carbon has been converted into carbon dioxide, right? So now we have to deal with whatever information we have in this block diagram. First of all, we need to fill this block diagram as usual, right? So again, there is air that contains oxygen and nitrogen. All right. So this is what we have for now. All right. This is all the information that we have from the question. And of course, we have the composition of flue gas, the dry product of combustion, that is carbon dioxide, oxygen, and nitrogen. We have these three. We have these three. So let's assume that this is equal to P. All right, this total is carbon dioxide plus nitrogen plus oxygen is P. Now, out of all these, which one, out of carbon dioxide, nitrogen, and oxygen, just think that which of these three can be most easily found by stoichiometry or by some other balance? Which one of them can be most easily found? So the answer to that is carbon dioxide. Since we have carbon here and we have carbon coming in from nowhere else, right? If we go for nitrogen, then we of course have nitrogen here and we have nitrogen here. We know about this nitrogen, but we don't know about this nitrogen. Similarly for oxygen, and we don't even know that how much oxygen is going to be consumed. All right, so there's more calculation required. So carbon, since carbon, all of it is converting into carbon dioxide. There's nothing else about this carbon. So we are going to use this carbon easily. All right. So what we are going to do, this equation that will be formed, that would be for carbon balance. All right, that is going to be for carbon balance. So carbon that is going in, it is going in as carbon, right? It is going in as carbon and it is coming out as carbon dioxide. So instead of making a material balance equation, it is better if we use stoichiometry, right? So we know that carbon, it reacts with oxygen to give carbon dioxide. That is what we are going to have. So carbon is 67.9 kg. So that's 67.9 by 12 gives you 67.9 by 12 kilomoles. And since this is 1:1 ratio, therefore 67.9 by 12 kilomoles of carbon are going to give you 67.9 by 12 kilomoles of carbon dioxide. Right? So carbon, that is going to be 5.658 kilomole. All right, 5.658 kilomole. So this carbon dioxide we have 5.658 kilomole. All right. Once we have carbon dioxide over here, then we'll go back and see the carbon dioxide is 14.5% in this P. And this percentage is given by volume. That means we can definitely take it as 14.15, right? 14.5 by 100 into P. That is the percentage of carbon in P. All right. So this is equal to whatever is the carbon here, right? So when we find P from here, you'll get it as 39.023 kilomole, right? That is what you're going to find. Then nitrogen, it is 80.8% of it. So nitrogen over here in this, it's going to be 31.531 because it's 80.8%. So 80.8 by 100 into this. So that would give you 31.531 kilomole. This is nitrogen. All right, and oxygen, it is given P 4.7%. So 4.7 by 100 into this. So that will give you oxygen as 1.834 kilomoles. All right, that is the oxygen over here. Okay. Now, once we have nitrogen here and nitrogen here, we have nitrogen in this part and we have nitrogen in this part. And we know that nitrogen is nowhere involved in any of the chemical reactions, right? So since nitrogen is nowhere involved in any of the chemical reactions, we can simply form a nitrogen balance equation, which is nitrogen in is equal to nitrogen out, right? Nitrogen in is equal to nitrogen out. Right, so nitrogen in, let's consider this as X. All right, so we'll get nitrogen in is 16 by 28, that is nitrogen from here, plus X is equal to nitrogen out, that is 31.531. All right, so from here we'll get X as 30.97 kilomoles. All right, so this is 30.97 kilomoles. All right. This is what we have got for nitrogen. Now, there is, as I told you, we can calculate oxygen supplied from nitrogen supplied. That is done by oxygen supplied is equal to nitrogen supplied into. Now, as I told you, whatever is in the LHS, we are going to keep that percentage on top. So that is 21 upon whatever is in the RHS, we are going to put that percentage on bottom. So 79. So nitrogen supplied into 21 by 79, that is 30.97 into 21 by 79. So that is going to be 8.23 kilomole, right? That is your result. All right, that is the oxygen supplied, 8.23 kilomole. All right. So once we have this information, then we can definitely understand more. We can definitely start on calculating the other things. So over here we have sulfur, that is 0.8 kg. We need to complete the block diagram. That's all. So sulfur is 0.8 kg. So in order to evaluate the sulfur dioxide form, we again going to use stoichiometry. So we know that sulfur plus oxygen gives us SO2. So sulfur is 0.8 kg upon 32 is its molecular weight. So since 1:1 ratio, therefore even sulfur dioxide being produced is going to be 0.8 by 32 kilomoles, right? So that is going to be 0.025 kilomole. All right, so I'll write it down over here, 0.025 kilomole. All right, and then we have hydrogen. We have hydrogen. So hydrogen in this is for 4.5 or 4 kg. So 4.4 kg. So therefore we are going to get H2 plus half O2. Once again, stoichiometry is going to give us H2O. So 4.4 by 2, and this would again give you 4.4 by 2 kilomoles of water. So that is 2.2 kilomoles. And then there is water present here already. So water present in the feed is equal to 12.9 upon 18 kilomole. So the total water that will be that we'll get in the flue gas is going to be 2.2 plus 12.9 by 18. That is over here 2.9167 kilomole. All right, that is what we have. All right, so this block diagram is complete now. This block diagram is complete now, right? However, there is just one thing that is not mentioned in this block diagram. Remember, when we draw a block diagram for combustion, we always need to specify percentage excess of air that is used. All right, so how to get that? So in order to calculate percentage excess, we always need percentage excess. The formula is going to be supplied minus theoretically required upon theoretically required, right? So now, since we have to calculate percentage excess of air, so that can be air supplied minus air theoretically required upon air theoretically required. And then if we multiply the numerator and denominator by 0.21, then we'll get air supplied into 0.21. That is oxygen supplied, because oxygen is 21% of air. So this can be same as oxygen supplied minus oxygen theoretically required upon oxygen theoretically. And using the same logic, we can also write it as nitrogen supplied minus nitrogen theoretically required upon nitrogen theoretically required. So remember, these informations are very important. All right, this is what is very important. All right, and of course supplied minus theoretically required is basically the excess. So we can say this is excess air upon theoretical air, right, which is nothing but excess oxygen upon theoretical oxygen, which is nothing but excess nitrogen upon theoretical nitrogen. So once you have all these things, these are all basically your tricks to solve certain problems. You know, certain problems, they might be very tricky, they might be, you know, slightly complicated. So in order to reduce your calculations, reduce your time you spend on each problem, we can use different ways. We can manipulate whatever information we have to get whatever we require. Okay, so all these things are quite important. So always keep a note of these things. All right, so now among all these six, which one is most easy? See, we already know oxygen supplied, right? And oxygen theoretically required can also be easily calculated. So obviously this formula is the easiest formula that you can get, you can use over here. So our next aim is to calculate the theoretically required oxygen theoretically required. Right, that is our main aim for now, to calculate oxygen that is theoretically required. All right, so once we have this, we'll be able to calculate the rest of the things. Okay, so now remember, this oxygen theoretically required is going to be oxygen theoretically required from air. All right, this you need to keep in mind. This oxygen is the theoretical amount of oxygen that is required. It's theoretically required from air. How much oxygen do you demand from air? Theoretically, how much do you need it from air? All right, so why have I said this? Because this coal already contains oxygen, right? It contains oxygen, so we don't need entire oxygen needed for combustion from air. We already have something, right? We already have some oxygen, so we'll use this, and extra oxygen that is needed for combustion, we'll ask that extra oxygen from air. All right, so that has to be kept in mind. So oxygen in the coal is given to be how much? 7.9 kg. So it's 7.9 by 32 kilomoles. All right, this is already in the coal. All right, then we need to calculate how much of it is theoretically required in the reactions. So over here we have, see, over here we have three combustion reactions taking place: reaction number 1, reaction number 2, and reaction number 3, right? These three combustion reactions are taking place, so we need oxygen from all the three reactions, right? So from the first reaction, as you can see, the ratio is 1:1:1, right? The ratio is 1:1:1. So the same moles of carbon are that are the number of moles of carbon that are reacting, the same number of moles we need for oxygen. So that is 5.658. All right, and same over here, we need 0.025 kilomoles of oxygen. All right, because same ratio, 1:1:1. And over here we need whatever moles of hydrogen are reacting, we have to we need half of them, right? 1:1. So we need half of the moles of hydrogen that are reacting. So 4.4/2 into 1/2, that is 4.4/4, that is 1.1 kilomoles. So oxygen in reactions, or oxygen required for reaction, or oxygen required for combustion, is going to be 5.658 plus 0.025 plus 1.1. All right, this is what is required for combustion. Therefore, oxygen theoretically required from air is going to be required for combustion minus the oxygen that is already there in the coal. All right, oxygen that is required for combustion minus oxygen that is already there in the coal. So oxygen that is required for combustion is 5.658 plus 0.025 plus 1.1, right? So that is equal to 6.783 kilomole. And oxygen that is already there in the coal is 7.9 by 32, right? 7.9 by 32, that is 0.247 kilomole. Therefore, oxygen required from air is going to be equal to 6.783 minus 0.247. That is 6.536 kilomole. All right, 6.536 kilomole. And how much of oxygen has been supplied by air? We already have that in the block diagram, 8.23 kilomole. Therefore, the percentage excess is going to be equal to 8.23 kilomole, that is supplied, minus 6.536, that is theoretically required from air, upon 6.536, that is theoretically required from air, into 100. So percentage excess comes out to be approximately 25.92%. Okay, 25.92%. This is what we require. All right, that is the percentage excess of air. So I'll go and mention it. Okay, now our block diagram is complete. Now let's go on to see what the problem has asked. They have asked the theoretical volume of air used at STP for complete combustion of 100 kg coal. So what is the air that has been supplied? 8.23 plus 30.97 kilomole, right? Air that is supplied is 8.23 plus 30.97. But theoretical volume of air they have asked. Theoretical air required. So there is 6.536 kilomole of theoretical oxygen, right? So since theoretical oxygen is 6.536 kilomole, that implies that theoretical air that is going to be required is 6.536 upon 0.21. We have already discussed why do we divide 0.21 over here. So I'll not just mention again. So 6.536 by 0.21 is going to be 31.124 kilomole, right? So that's your theoretical air that is required. This is the number of moles. We need to calculate volume at STP. So at STP, we know that pressure is 1 atm and temperature is 273 Kelvin, right? So we are going to use the ideal gas equation, V equals to nRT by P. N is the number of moles, that is 31.124 kilomole, into R is, now again pressure is in atm, so we are going to use R as 0.08206 meter cube atm per kilomole Kelvin, right? Into temperature is 273 Kelvin, and when we divide this by pressure, that is 1 atm. So you can see atm, kilomole, Kelvin, Kelvin. If it gets cancelled, so finally we'll get the theoretical volume of air that is required. It's 697.25 meters. Right. So as I told you, once your block diagram is complete, there's nothing more you need to do. You just need to manipulate whatever values you have. So that's what we did. We just used the number of moles that we had from the block diagram and we calculated the volume, right? And second part, they're asking the percentage excess of air used. The percentage excess we've already calculated as 25.9, right? So this is your part A and this is your part B. So hope you could understand what we did in this problem. If you people have any doubts, if you people could not get it, please pause the video and then go back and see this video again, whatever has been told about this particular problem. Then we move on to the next problem, that is example number 3. Pause the video and try to solve this problem yourself. Okay, so let's see how this problem is done. A petrol sample contains 80% carbon and remaining hydrogen on mole basis. If air supplied is 10% excess, calculate the molar composition of the flue gas. This is quite easy, but let's see. So I'll draw the block diagram for this. All right. So there's mole basis. So we are going to take basis as 100 kilomole petrol. All right. Now this 100 kilomole petrol, it contains 80 kilomole carbon and hydrogen is 20 kilomole. The remaining is hydrogen, so 20 kilomole is going to be hydrogen. Right. Now air that is supplied, it is in 10% excess. All right. 10% excess. All right. And over here in calculate the molar composition. So again, there has been no mention about incomplete combustion. So we are going to assume that all combustion is complete. So we'll get carbon dioxide, we'll get water, we'll get nitrogen, and we'll get oxygen. Right. So that's going to be our this thing. Right. So now basic calculations. So carbon plus oxygen gives you carbon dioxide, and the second reaction is water. So hydrogen plus oxygen gives you water, right? So there's 80 kilomole carbon, so that would give you 80 kilomole carbon dioxide as it is, right? Then there is 20 kilomole of hydrogen, so it would give you 20 kilomole of water. So 20 kilomole over here, right? Now, then we have oxygen. So let's calculate the theoretical oxygen demand. So theoretical oxygen demand is going to be oxygen required here plus oxygen required here. Now, unlike the previous question here, no oxygen is present in the fuel. So all the oxygen that we demand is from the air, right? So theoretical oxygen demanded is 80 kilomole for carbon and 20 by 2, that is 10 kilomole for hydrogen. So it's going to be 80 kilomole plus 20 by 2, that is 10 kilomole. So that is going to be 90 kilomole of oxygen is theoretically demanded. Now, since oxygen is 10% extra, so therefore oxygen supplied is going to be 90 into 1.1, right? 90 into 1.1, that is 99 kilomole. So 99 kilomole of oxygen is going to be supplied, out of which obviously we are going to use 90 kilomole in these reactions. So we'll get 90. So when we do oxygen balance, the equation that we discussed, so oxygen balance gives you oxygen in minus oxygen out is oxygen consumed. So oxygen consumed, oxygen consumed is basically 80 plus 10, so that is 90. So oxygen out is going to be 99, that is oxygen in, minus 90, that is oxygen consumed. So that is 9 kilomole, right? So 9 kilomole is going to be here. Although now, since we have done so many problems, we have been acquainted with this method. So you can just directly, instead of writing these equations, you can directly get this as 9 kilomole. That's not an issue. You just need to subtract the supplied, subtract the used oxygen from the supplied oxygen to get the oxygen that is going to be here. All right. And then nitrogen, whatever is here in the supplied air, the same amount of nitrogen is going to be over here, right? So nitrogen supplied, we discussed how to get nitrogen supplied from oxygen supplied, that is oxygen supplied into 79 by 21. Right? So nitrogen, you'll get it as 372.43 kilomole. So that is 372.43 kilomole. That nitrogen you will get over here. 372.43 kilomole. All right. So now we have to give the analysis. So when we do the gas analysis, we are going to have our components here. Components include carbon dioxide, nitrogen, oxygen, and water. Right. Then we have moles. So carbon dioxide was 80 kilomole. Then water was 20. Nitrogen was 372.43. And this was 9. Right. So altogether the moles are going to be 481.43. Right. Therefore, the mole percent, it is going to be 16.62. This upon this into 100. For nitrogen, it's going to be 77.36%. Then for oxygen, it's going to be 1.87%. And finally, for water, we are going to have 4.15%. Right? So when we add all of them, they will give you 100%. All right. So that's all about this question. It was a very easy problem. No need to worry. Now we come to example number 4. Go ahead, pause the video and try to solve this problem. So let's see how this problem is done. Dry flue gas composition shows 10% carbon dioxide, 8% oxygen, and remaining nitrogen. Find the composition on wet basis and the percentage excess of air supply. So this is what we have. Carbon dioxide is 10 kilomoles, oxygen is 8 kilomoles, and nitrogen is 82 kilomoles. All right. So let's see. I don't know my fuel over here. Right. I don't have any idea about my fuel. All right. This is a slightly different kind of question. So let's see. Then air over here, it contains oxygen and nitrogen. Okay. And then over here, you have carbon dioxide, oxygen, nitrogen, and since we have to calculate it on wet basis, so we'll also be having water. So assume that we have 100 kilomole of dry flue gas. All right, dry flue gas means excluding water. All right, so carbon dioxide is going to be 10 kilomoles in that case. Nitrogen is going to be remaining, that is 82 kilomoles. And oxygen is going to be 8 kilomoles, right? We don't know about water, okay? That is what is given in the question. Okay, now whatever is the nitrogen here, that would be the nitrogen over here. So it is going to be 82 kilomole, right? That is going to be 82 kilomole. Now oxygen that is supplied over here, it's going to be nitrogen supplied. Nitrogen supplied, that is 82 into 21 by 17. So oxygen supplied is going to be 21.8 kilomole. Right. So this is 21.8 kilomole. Okay. So now this is going to be this. Right. Now oxygen over here is 8 kilomole. Right. So that means oxygen consumed is 21.8, that is input, minus 8, that is out. This is the amount of oxygen that is consumed. This you can get by oxygen balance. All right. So oxygen consumed is going to be 21.8 minus 8 kilomole, that is 13.8 kilomole. Now let us assume that we have carbon and hydrogen in this fuel. So carbon will burn to form carbon dioxide and hydrogen will burn to form water, right? Now, carbon dioxide, we know it's 10 kilomole over here. So we know that we'll be having 10 kilomole carbon here. And for that, we'll be using 10 kilomole of oxygen. Water, we have no idea. All right, so we'll just leave water. So oxygen required in carbon or oxygen used to burn carbon is 10 kilomole. Therefore, oxygen to burn hydrogen is going to be what? The total oxygen that is consumed is oxygen burnt to consume, oxygen consumed to burn carbon plus oxygen consumed to burn hydrogen. So oxygen consumed to burn carbon is 10 kilomole. Therefore, oxygen consumed to burn hydrogen is going to be 13.8 minus 10. That is 3.8 kilomole. This is the amount of oxygen to burn hydrogen, right? So if 3.8 kilomole of oxygen is there to burn hydrogen, then 3.8 into 2 is going to be the water form, that is 7.6 kilomole, and over here as well it's going to be 7.6 kilomole hydrogen. All right, so once we know that, now can we find the wet flue gas analysis? So now the total flue gas we have is 107.6 kilomoles, right? So when we perform the wet flue gas analysis, so we have carbon dioxide, we have oxygen, we have nitrogen, and we have water. So moles of carbon dioxide were 10, oxygen were 8, nitrogen were 82, and now we have water, that is 7.6. So in total we have 107.6 kilomoles. All right, so mole percent is going to be 9.3, then this is going to be 7.4, this is going to be 76.2, and this is going to be 7.1. Right? So when you add, you get 100%. All right. This is the wet flue gas analysis, and then we have to calculate the percentage excess of air. So as I told you, oxygen supplied minus oxygen theoretically required. Theoretically required is oxygen consumed. That is 13.8. Right. So oxygen supplied as 21.8 kilomole minus oxygen that has been consumed is 13.8 kilomole, right? 10 plus 3.8, 13.8 kilomole upon oxygen theoretically required into 100. All right. So that gives you the percentage excess of air as 57.97%. So I guess that's all what we had to calculate in the composition on wet basis and excess. So that's all. All right. So this was slightly different. It was not difficult. It was slightly different. You needed to go the other way. All right. Because so far the questions that we've done, we've always taken basis for the fuel, right? We've always taken basis for the fuel. That okay, we have 100 kg of fuel or we have 100 kilomole of fuel. But this time what we had was a different type of question where they had given composition of the dry flue gas. So we had to take 100 kilomoles of dry flue gas. Correct? 100 kilomoles of dry flue gas. One more thing. The reason why we took here as 100 kilomole, because as I told you, it's a gas, right? So gas composition is generally, it is given in mole percent. All right. If it would have been a solid, then we would have taken it in weight percent, right? That is the reason why we took our basis as 100 kilomole. All right. So make sure that you don't get confused in these small things. All right. So once we are done with this, we'll move on to the next question. Go ahead, pause the video and try to solve this problem yourself. So let's see how this problem will be solved. This time we have a different fuel. We have a hydrocarbon. All right. So we have ethane. So here the concept goes slightly different. All right. So nothing is going to change as such. You're just going to change the stoichiometry. All right. Unlike the other questions where we were given the composition. So we could directly say that, okay, whatever carbon we have, it's going to react with oxygen. Whatever hydrogen we have, it's going to react with oxygen to form water. Whatever sulfur we have, it's going to react with oxygen to form sulfur dioxide. So we had three different reactions, right, to calculate the oxygen demand, theoretical oxygen demand. But now, since we have only one particular component, that is ethane, so in one reaction itself, we can get the carbon dioxide and water that is going to be produced. All right. So ethane is burnt with 25% excess air to form carbon dioxide and water vapor. Calculate the flue gas composition leaving the furnace and the quantity of gas which will be produced per kg of ethane burnt. All right. So that's your problem. So since we have to calculate everything per kg of ethane burnt, right? So we are going to take this as our basis, that we have 1 kg of ethane, all right? Basis we have that we have 1 kg ethane. Again, one question you might have, that why did not we take it as 1 kilomole? Why didn't we take it as 1 kilomole? Because ethane is a gas. It's a gaseous fuel. We should have taken 1 kilomole. 1 kilomole or 100 kilomole basis is taken only if you have composition, right? If I would have given, suppose we have 25% ethane, 10% methane, something like that. In that case, I would have taken that, okay, we have 100 kilomole of mixed gas. But right now we only have ethane. So no, it doesn't matter if we take kilomoles, if we take kg. So we go on the question, right? So here it is given that we have to calculate it per kg of ethane burned. So we need to calculate it. We need to take the basis as 1 kg. So it doesn't matter if we take 1 kilomole or 1 kg, right? So that's why. Okay. So 1 kg of ethane is our basis. So that means moles of ethane are going to be 1 upon molecular weight of ethane. Ethane is C2H6. So 12 into 2 plus 6, that is 30. So 1 upon 30, that gives you 0.033 kilomole. All right. So that many kilomoles of ethane. All right. This is what we have. Now let's see. The first step in this kind of a problem is your stoichiometry. Stoichiometry is very important. So we have ethane, C2H6 plus oxygen gives you CO2 and water. Now remember, balancing these equations is tiresome at times, right? So make sure you are carefully balancing this equation so that you don't face problems later. So this is how I have balanced the equation. All right. If you want, you can also multiply this 2 everywhere. All right. That is also fine. You don't need to get confused. That's all. All right. Any way you can do. Okay. It's stoichiometry. It's mathematics. It can be done any way. You will get the same answer. All right. So it's C2H6 plus 7 by 2 oxygen gives you 2 CO2 plus water, 3H2, right? Now ethane is 0.033 kilomole, right? So on the basis of that, carbon dioxide produced is 0.066 and water produced is 0.099, right? This into 2 and this into 3. Right, and oxygen that would be required to react, it is going to be this into 7 by 2, so 0.1167. All right, so this oxygen that is needed, this becomes your theoretical oxygen demand. So that is 0.1167 kilomole. All right, so once we have theoretical oxygen demand, so in that case, we are going to get whatever the other things we have. So it is given that 25% excess air is there. So oxygen supplied is 0.1167 into 1 plus 25 by 100. So 1.25. Right. This is the oxygen supplied. So that is 0.146 kilomole. Right. Then nitrogen supplied is going to be oxygen supplied into 79 by 20. Right. 79 by 21. So nitrogen supplied is 0.55 kilomole. All right, that is going to be nitrogen supply 0.55 kilomole. Okay, so right. So now oxygen that is theoretically demanded was 0.1167, and that is also equal to the oxygen that is consumed. So oxygen in flue gas is going to be 0.146, that is oxygen that was supplied minus oxygen that was consumed. Right. So that is equal to 0.0293 kilomole. All right, 0.0293 kilomole. That is oxygen in flue gas. All right. So then, once we are done with this, so now we know we have in the flue gas, we'll be having carbon dioxide, we'll be having water vapor, and we'll be having oxygen and nitrogen. So to find the composition of flue gas, we'll get carbon dioxide, water, nitrogen, and oxygen. Correct. So that's going to be the composition. Then moles over here are going to be 0.066. Then this is going to be 0.099. Then this nitrogen supplied is going to be whatever is going to be in the flue gas, right? Because it is not involved in any reaction. So it's going to be 0.55. And then oxygen, we calculated it as 0.0293. This was in the flue gas. So mole percent is going to be this by total. Total moles is 0.7443. Right. So mole percent is going to be indivisible by total into 100. So this is going to be 8.9%. This is going to be 13.3%. Then this is going to be 73.9%. And this is going to be 3.9%. Okay, this is the flue gas combustion. Anything else that was asked? No, that was all. Calculate the flue gas composition leaving the furnace and the quantity of gas which is leaving. So this is the quantity of gas and this is the flue gas combustion. All right. So hope you people are clear with whatever has been done about this question, right? So then we move on to the next problem. Example number 6. A water gas has the composition carbon monoxide 25%, carbon dioxide 5%, nitrogen 70%. This gas is burned with 30% excess air required for complete combustion. If the combustion is 95% complete, calculate weight and composition volume percent of the gaseous products formed per kg of gas burned. Go ahead, pause the video and try to solve the problem itself. So let's solve this problem. Now over here, they have given us that we have to find everything per kg of gas burned. But they have not mentioned whether the composition is going to be in weight percent or it is given in mole percent. So now, since it is a gas, that is why we are going to take this composition in mole percent. All right. So we are going to go ahead with our basis as 100 kilomole of water gas. All right. So now this is our chamber. It contains carbon monoxide, that is 25 kilomole. Then carbon dioxide, which is 5 kilomole. And of course, nitrogen, that is 70 kilomole. All right. And air is supplied 30% excess. So air is 30% excess. And then the products of combustion, we'll have carbon monoxide, carbon dioxide, nitrogen, and unreacted oxygen. Right. So this is all what we have with us. Okay. So now let's see how to solve this problem. So first of all, the only reaction that is going to take place for combustion is this one. Carbon monoxide plus half O2 gives you carbon dioxide. This is the only reaction that is going to take place. So since combustion is 95% complete, since combustion is 95% complete, carbon monoxide converted, the carbon monoxide that is going to be converted is only 95% of this. All right, 95% of this, so that is 23.75 kilomole. So 23.75 kilomole of carbon monoxide is going to participate here, and it would give you 23.75 kilomoles of carbon dioxide. So that is here, plus 5 kilomole, we already have carbon dioxide. So in total, we'll get carbon monoxide, carbon dioxide as 28.75 kilomoles. All right. Then carbon monoxide left is going to be 5%. So 25 into 0.05, that is going to be 1.25. Right. So 1.25 kilomole of carbon monoxide is going to be left. Now our desired reaction is this, and what we desire is that all the carbon monoxide, it gets converted into carbon dioxide. So theoretical oxygen demand is going to be the oxygen that is required to convert all this carbon monoxide into carbon dioxide. So carbon monoxide is in total 25 kilomole, and per kilomole we require 1/2 kilomole of oxygen. So 25 into 1/2, that is 12.5 kilomole oxygen. That is the theoretical oxygen demand. Okay, so since oxygen is supplied in 30% excess, so oxygen supplied is 12.5 into 1.3. Right. So oxygen supplied is going to be 16.25 kilo. Right. Oxygen consumed. Now remember, so far in most of the questions, what we have done is we have considered oxygen consumed is equal to theoretical oxygen demand. But this time, oxygen consumed would only be the oxygen that would convert this much, 23.75 kilomole of carbon monoxide into carbon dioxide. So it's going to be 23.75 by 2. All right. Oxygen consumed is going to be 11.875 kilo. All right. That is going to be oxygen consumed. Therefore, oxygen in flue gas is going to be 11 point, sorry, not 11 point. Oxygen supplied 16.25 minus oxygen consumed, that is 11.875. Right. So that is going to be 4.375 kilo. So that is oxygen. So 4.375 kilomole. All right. Then, since oxygen supplied is 16.25, therefore nitrogen supplied is going to be 16.25 into 79 by 21, right? So nitrogen supplied is going to be 61.131 kilomole, right? And we already have 70 kilomoles of nitrogen in the water gas. So nitrogen in the flue gas is going to be nitrogen from here plus nitrogen in the air, that was 61.131 kilomole. So that is going to give you 131.131 kilomole of flue gas, and oxygen in the air was 16.25. So our block diagram is complete. Now what they need to calculate is calculate the weight and composition of the gaseous products. So, composition. First, let's go ahead with the composition. So component: carbon monoxide, carbon dioxide, oxygen, and nitrogen. Right. So moles of each carbon monoxide was 1.25. This was 28.75. And oxygen was 4.375. And nitrogen was 131.131. So when we add all of them, we'll get 165.506. Right? That's going to be the moles. 10 mole percent is of course 0.0075. Actually, this is not mole percent, this is no fraction. Multiply this by 100. So that gives you 0.75% is carbon monoxide, and 17.37% is carbon dioxide, then 2.64% is oxygen, and 79.23% is nitrogen. So we add, this is what we're going to get. Then weight, so for that we need molecular weight of each. So molecular weight is going to be carbon monoxide is 28. So we've taken the molecular weight of each. Then we are going to find the weight. So weight is moles into molecular weight. So it's going to be 1.25 into 28. That is going to be 35. Right after that. So we have got weights, individual weights. Therefore, we get the total as 5,111.668 kg. All right, this is what we have. And then accordingly, we can do the further. Then they have asked us to calculate weight of the gaseous products per kg of gas burnt. What we have taken 100 kilomole of water gas, right? So basically we have to find weight of gases, flue gas, upon weight of water gas burnt. All right. So weight of gases we have calculated as 5,111.668. This we need. So we have 100 kilomole of water gas. All right. Not H2, not at all H2. So 100 kilomole of water gas. Right. Now, water gas contains 25% carbon monoxide, carbon dioxide is 5%, and nitrogen is 70%. This is mole percent. So from here, we can obviously get the average molecular weight of water gas. So that is going to be sigma xi mi, right? So it is 25% carbon monoxide, so 0.25 into molecular weight of carbon monoxide, plus there is 5% carbon dioxide, so 0.05 into molecular weight of carbon dioxide. Plus there is 70% nitrogen into its molecular weight. So this average molecular weight that we are going to get, it is 28.8 kg per kilomole. Therefore, weight of water gas is going to be 100, that is moles, into molecular weight of the gas, that is 2880 kg. All right. Now over here we have calculated the average molecular weight, but what we could do, what else we could do is, we already know over here that these many kilomoles of each carbon monoxide, carbon dioxide, and nitrogen are present. So what we could have done is, we could have individually multiplied these moles by their molecular weights. So 25 into molecular weight of carbon monoxide, plus 5 into molecular weight of carbon dioxide, plus 70 into molecular weight of nitrogen. So when we would have added them, we would have got the total weight, right? So instead of getting the average molecular weight and then multiplying the moles of water gas by the average molecular weight, this is an alternative method. All right, we could simply find weight of individual components and we could have added on. So you would have got the same thing, of course, right? You would have got the same thing. That's not at all. All right. So once we have got this, so we are going to substitute this value over here. So this is going to be 2880. So this is going to be 1.775 kg flue gas per kg of water gas burnt. All right, that is your answer. All right. So hope this problem was clear. All right. So when this is clear, we move on to the next problem, that is example number 7. A kiln is fired by a producer gas having the volumetric composition carbon monoxide 25%, volumetric composition as in mole percent. All right. Hydrogen is this, oxygen, carbon dioxide, and the rest is nitrogen. The combustion is only 98%. Calculate the composition. Molar composition of the dry flue gas is formed, and weight of the water produced if 20% excess air is supplied. All right. So go ahead, pause the video, and try to solve this problem yourself. Okay, so let's try to solve this problem. So we have our kiln. We are going to keep basis since it is volumetric composition, that is mole percent. Therefore, basis is going to be 100 kilomole gas. All right, 100 kilomole of producer gas. So this is going to be carbon dioxide, sorry, carbon monoxide. Carbon monoxide is 25 kilomole. So carbon monoxide is 25 kilomole. Then hydrogen is 11 kilomole. All right, oxygen is 0.4 kilomole. Carbon dioxide is 5.6 kilomole. And nitrogen is the remaining, so that is 58 kilomole. All right, so hope this part is clear, right? So 5.6, 25, 11, 0.4, and 5. Right. Okay. So once we have done this, then we'll go for the anything else that is given. Okay. Air is 20% excess. So we have air, which is 20% excess. Okay. And over here, we are going to get carbon monoxide, carbon dioxide, oxygen, nitrogen, and water. All right. So let's start. Once again, they have given combustion is only 98% complete. That means 98% of carbon monoxide is going to form carbon dioxide, right? And the remaining carbon monoxide is going to be left. So 25 into 0.02, right? 25 into 0.02. That is the amount of carbon monoxide that is going to be left, right? So 25 into 0.02 is 0.5 kilo, right? 25 into 0.02 is 0.5 kilograms. That is the amount of carbon monoxide left, right? Remaining 98% has been burned to carbon dioxide. So 25 into 0.98, because of stoichiometric ratio 1:1, we are going to get the same amount of, if 25 into 0.98 kilomoles of carbon monoxide have burned to form carbon dioxide, then we are going to get 25 into 0.98 kilomoles of carbon dioxide. And apart from that, we also have carbon dioxide from here, so that is 5.6. So altogether, we are going to get 25 into 0.98 plus 5.6 carbon dioxide is going to be 24.5 kilo, right? 24 point, no, just a minute, I'm sorry. It's just this, we have not included carbon dioxide. So it's going to be carbon dioxide that is going to be there, that is 24.5 plus 5.6, whatever carbon dioxide had come from here, right? So 24.5 is basically this, and 5.6 is added to it. Okay, so we are going to get carbon dioxide is 30.1 kilo, all right? 30.1 kilo. Okay, all right. Then once we have 30.1 kilomoles of carbon dioxide, then we are going to get oxygen and nitrogen over here. So we know that theoretical oxygen required from air is going to be oxygen oxygen that is theoretically required, that is 25 into 0.98 by 2 minus whatever oxygen is already present, that is 0.4. This much oxygen is theoretically required from air, right? So 25 by 2. Oh, just a minute. Plus even hydrogen is there, right? So hydrogen plus after 2 gives you H2O. So hydrogen is 11. This is going to be 5.5, and this is again 11, right? So plus 5.5, right? Just a minute, sorry. See, we need, first of all, let's see what is the theoretical oxygen required, not from air, in general for this chemical reaction. All right, there's a slight confusion. So theoretical oxygen required is going to be, as I told you, what we want is that all the carbon monoxide, it should be converted to form carbon dioxide, right? So 25 kilomole of carbon monoxide is there. So we want it to convert entirely into carbon dioxide. So for 1 kilomole of carbon dioxide, half kilomole of oxygen is required. So it's 25 by 2 plus, for 11 kilomoles of hydrogen, we need 11 by 2 kilomoles of oxygen, right? So this is the theoretical required oxygen from both the reactions, right? That is 25 plus 11 by 2, that is 18 kilomole. This is the required oxygen. All right. Now from air, theoretical oxygen required from air is going to be 18 minus whatever oxygen is already available, that is 17.6 kilomoles. right? This is the oxygen that is required from air. Now, since it is 20% excess, therefore, oxygen supplied is going to be 17.6 into 1.2. All right, 17.6 into 1.2, that is 21.12 kilomole. So oxygen supplied over here is 21.12 kilomole, right? And nitrogen supplied is going to be 21.12 into 79 by 21. So nitrogen supplied is 79.45. Right, nitrogen supplied is 79.45 kilo, right? So that's going to be here 79.45 kilo. Okay. So nitrogen in the flue gas is going to be 79.45. That is oxygen that is supplied from here, plus oxygen already there in the gas that has been supplied, that is 58 kilomole. So it's all together, it's going to be 137.45 kilomoles. Right? Then water that is going to be there, it's 11 kilomole. Right? Since there is 11 kilomoles of hydrogen, all of it is going to be converted into water. So you are going to get 11 kilomoles of water. Finally, oxygen in the flue gas. Oxygen in the flue gas is equal to oxygen that is supplied, that is 21.12, minus oxygen that is used, right? Oxygen that is consumed. So that is equal to 25 into 0.98 by 2. Right? Plus 5.5 kilograms. All right. This is for carbon monoxide, and this is for hydrogen. Right? So the oxygen in flue gas, it's going to be and also wait, also oxygen inlet is 0.4 kilovolts. So oxygen in minus oxygen consumed. So in total, it's going to be 3.77 kilovolts. That is going to be oxygen in flue gas. Right? So we have to calculate the oxygen, the composition, the volumetric composition. So that you can do, you simply need to, since you need to calculate the volumetric composition of dry flue gas, you only need to consider these, right? You only need to consider these. And since we need to calculate the weight of water, so weight of water produced is 11 into molecular weight of water, that is 18. So it is going to be 198 kg. All right, 198 kg of water is going to be produced. And remaining, the composition of flue gas can be simply calculated. We are going to add all of them, all the moles, and we are going to calculate the mole fraction. All right, so that's how you can simply calculate the composition. Then we move on to the last problem for combustion. That is example number 8. This is a very important and very interesting kind of example. So go ahead, pause the video and try to solve this problem yourself. Okay, so let's see how this problem is solved. So first of all, let's draw our block diagram. So a basis, again, since we have a gaseous mixture of methane, ethane, propane, so we are going to take 100 kilomole of mixture. Okay, so over here we have methane, ethane, and propane, right? So methane is 15%, so it's going to be 15 kilomole. Then ethane is 45%, so 45 kilomole, and propane is 40%, so 40 kilomole, right? Now let's write down the stoichiometries related to these each of them. So we have methane, which burns with oxygen to form CO2 and water. So it's going to be that. Then ethane, it burns with oxygen. So, and then we have propane, that all right. So that is going to be our stoichiometry, reaction stoichiometry. So if we have 15 kilomole of methane, that's going to form 15 kilomole carbon dioxide. If we have 4 and 30 kilomole water, it is going to use 30 kilomole of oxygen, right? If we have 45 kilomole of ethane, then we are going to get 90 kilomole carbon dioxide and 135 kilomole of water. And oxygen that is going to be used in that case is 45 into 7 by 2, that is 157.5 kilomole. And ethane, propane, it's 40 kilomole. So 120 kilomole, 160 kilomole water, and oxygen that is going to be used is 200 kilomole. All right. So over here, we are going to get carbon dioxide, water, unreacted oxygen, and nitrogen, right? So now carbon dioxide we have calculated 15 plus 90 plus 120, right? 15 kilomole plus 90 kilomole plus 120 kilomole. So that is going to be 225 kilomole. And water that we are going to get, it's 30 plus 135 plus 160, that is equal to 325 kilomole, right? That's about these two. All right. Then we also have air here that comes in, right? And then they have said that the dry flue gas composition shows 10% carbon dioxide. So dry flue gas composition means apart from water, the remaining. So it has 10% carbon dioxide. So that means 0.1 into, let's say, dry flue gas is X. So 0.1 into X is 225. So X you are going to get as 2250 kilomole. Right. So when X is 2250 kilomole, then that means since carbon dioxide is a part of this, so let's consider oxygen plus nitrogen in the flue gas to be Y. So you have Y plus carbon dioxide is 2250. Therefore, Y you will get it as 2250 minus 225. That is equal to 2025 kilo. All right. This is what you are going to get. All right. Then let's see theoretical oxygen demand for this. So theoretical oxygen demand is equal to 30 plus 157.5 plus 200. So that is 387.5. That is 387.5 kilo. All right. Then from here, we can get theoretical nitrogen demand. We'll just understand why we need this theoretical nitrogen demand. So theoretical nitrogen demand is going to be 387.5 into 79 by 21. That is equal to 1457.74 kilo. Right? That is going to be theoretical nitrogen demand. And therefore, we'll get theoretical air is equal to 1845.24 kilomole. We simply add these two, right? So we'll get theoretical air, that is 1845.24 kilo. All right. So once we get this, then over here, Y that we have, it is actually all the nitrogen that has been supplied, plus excess of oxygen, apart from oxygen that has been used, excess of oxygen that was there. So Y is basically what? All the nitrogen that has been supplied, that means nitrogen theoretical plus nitrogen excess, right? And oxygen that is over there, that is only the excess oxygen, right? So we have just calculated theoretical nitrogen as 1457.74. So when we are going to get Y is 2025. So when you're going to write 2025 is equal to 1457.74 plus excess nitrogen plus excess oxygen. So you're going to get excess nitrogen plus excess oxygen is equal to 567.26 kilo, right? Now, excess nitrogen and excess oxygen is basically what? It is excess air, right? It is basically excess air. So excess air is 567.26 kilo, right? 567.26 kilo. Now, if you remember, we had in this video itself, we did a problem where I discussed 6 formulas with you people regarding excess air, right? Percentage excess, right? We discussed 6 formulas. So one of the formulas, if you remember, it was percentage excess is equal to excess air upon theoretical air into 100. So excess air we have got it as 567.26 kilo. And theoretical air we have calculated as at 1845.24. So 1845.24 into 100, right? So 567.26 upon 1845.24. So that is equal to 30.742%. That's what we had to calculate. We only had to calculate the percentage of excess air used and also the star gas analysis. So now once we have the percentage of excess air used,